Welcome to our third module dedicated to quantum factoring. Today we're going to discuss the quantum phase estimation algorithm, which is a reason we can introduce the quantum Fourier transform, which is the key component of quantum factoring. The problem of quantum phase estimation is that given the input state psi under this form, where you have an unknown phase omega, you want to find omega. Now, the idea here is that if you measure the state, it will give you the same outcome as if it were a uniform superposition over all possible y's between 0 and to the n minus 1. So something needs to be done to the state in order to measure the information in the phase. The two main cases that we will study today are the special case where the phase is of the form x over 2 to the n for x an integer, and the case where omega is an arbitrary real number. In the latter case, of course, we're only going to be able to provide an approximation, a rational approximation of that real number. So, first example, the simplest one, is if you are looking at this problem on one qubit. So this is the shape of psi, and in the case where you're looking for a rational phase, then this x1 is going to be 0 or 1. And so how do we do this? Then notice that if you do h times psi, what you're going to get is 1 over square root 2. So it's 1 over square root 2 times 0 plus 1 in the case of x1 equals 0, and h 0 minus 1 in the case of x1 equals 1. And so here we will obtain h of plus, which is 0, which is x1, of course, and here we will obtain, so h of minus, which is 1, and that is also x of 1. So measuring the result, measuring the qubit after applying the Hadamard gate solves the problem in one qubit. Now let's see how things get a tad more complicated when we have the same problem on 2 qubits. So here we assume, again, this is still the simpler case of phases that are rational numbers. Here we use this notation where we have a notation in binary. So this really means that we have x1 times 2 plus x2 times 2 to the 0, if you wish, divided by 4, okay? And we're going to use this notation throughout the lecture, okay? Now, the important thing to realize here is that this input state is a product state, okay? This is our product state. The first qubit has the exact same shape as the one for which we were able to solve the quantum phase estimation just by one Hadamard gate, because this is exactly 1 over square root 2 of 0 plus minus 1 to the x2 times 1. So this, on the first qubit, you can apply the trick that we saw previously in order. So if I do h of first qubit, what do I get? I get exactly x2, okay? And here, on the second qubit, well, if by chance, that is not guaranteed, but if x2 happens to be 0, then what do we get? We get another case of a one qubit quantum phase estimation, because what we get here, if x2 equals 0, we get this state here, which again, with the Hadamard gate, we're applying the action of the Hadamard gate once, we get x1, okay? So really, The only problematic case is if we have x1, x1 equals 0, in which case, if x2 equals 0, and in which case we're going to have to do something different, okay? So, if x2 equals 1, what do? We need to erase first the contribution of x2 in the second qubit, okay? So what do we have here? We have a rotation gate that we can apply to do this purpose, for this purpose, and in particular, we're going to actually be using the inverse of that gate. This is a family of gates. So we have R sub k that we're going to be using, which is 1, 0, 0, 2 to the, it's an e to the 2 pi I over 2 to the k. Okay, and this happens to be equivalent to the rotation around the z-axis of angle 2 pi over 2 to the k, okay? So they really are rotation gates, but we need to formulate, we need to use their equivalent, the matrix that is equivalent to them under this form to really see how we're going to be able to erase the contribution of the second term in the phase. So if I apply this, the inverse of this gate, to the state of the second qubit, in the case where I have in the phase 2i pi 0, x1 and 1, so if x2 equals 1, what do I get? Well, the 0 basis vector gets untouched, okay, and a minus 2 pi I 0.01 is applied to the phase of the second basis vector. So what we get is 0 plus exponential 2i pi 0.x1 times 1. And with that, we know that we're going to be able again to solve the quantum phase estimation by applying the Hadamard gate after the inverse of the rotation. So we again reduced ourselves to the case of the 1 qubit case. So here is the this is the state then that we need to this is the circuit that we'll use in order to solve the quantum phase estimation problem in the 2 qubit case when the phase is known to be a rational number. Okay, so here after the first Hadamard gate, what we get is the state x2. Okay, now in the case where x2 equals 0, we do not need to do anything to the second qubit, because then it will go through the Hadamard gate without having and then produce x1. Okay, and so that's why in the case of x2 equals 0, the controlled rotation, so the control inverse of R2 is not going to be activated. However, when x2 equals 1, then this is going to be activated, and it will first produce here the state 1 over square root 2, 0 plus exponential 2 pi I 0 x1, and then here after the Hadamard gate we get the state x1. Okay, so really the important ingredient is the controlled rotation. It's only activated when the state x2 is 1. If it's 0, it leaves the second qubit untouched, and then the Hadamard gate finishes the job. So like I said before, the rotations, we're going to be using R sub k, and the rotations are a special case of z rotation around the, rotations around the z-axis of angle theta. Here, theta is always going to be a 2 pi over 2 to the k, okay? Now, in general, these rotations aren't going to be in our gate set, right? You have special cases like the S or the T gate. There's in rotations of angle 2 pi over 2 to the k for small k, but then when k grows, these rotations are going to be outside of our gate set. So what do? Well, we can approximate them. That's really the only trick that we can apply because there's infinitely many of them. And so we know from the Solovay-Kitaev results that we can provide efficient approximations of R sub k with Clipper plus T gates, all right? And that's just really all we need. So for example, here you have an approximation of a z rotation of angle pi over 128. So what is this? This giant product of H, S, and T gates is close to the rotation of angle pi over 128. It's technically known to be at least, at most at a distance of 1 over 10 to the 10, okay? But of course, this requires advanced calculation methods, okay? So this is outside of the scope of this course, but you would need to use computer algebra techniques to find such an approximation of the z rotation of angle pi over 128, okay? But we know how to do that, and we know how to do that systematically. We're not relying on chance. There are explicit methods to produce such approximations. Now, what happens once you have a phase of form x over 2 to the n, and then we're dealing with n qubits? Well, the input state, psi, still is a product state, and we can verify that it factors as this product, the tensor product that we have here. And then what's really important here is that the first term is exactly one for which we find xn with the Hadamard gate. The second one is really the 2-qubit case. And then we increase the number of terms in the phase, which really means that we're going to just generalize the previous approach to n qubits. So the last one will have plenty of rotations, plenty of control rotations to eliminate all the potential xn, xn minus 1, xn minus 2, etc. to get a 0.x1 in the phase, okay? So let's see what it could look like in 3 qubits, okay? So this is the case of 3 qubits. What do we have here after the Hadamard gates? We have x3, okay? Now, what we want to recover is the state x2. We would like to have it here. However, first, we need to remove x3 if x3 equals 1. If x3 equals 0, then we have our state 1 over square root 2 0 plus exponential 2 pi I 0.x2 times 1, which after Hadamard transform would get us exactly x2. So if x3 equals 1, then the controlled rotation will produce either way 1 over square root 2 0 plus exponential 2i pi 0.x2 times 1, okay? And then here we get x2 after the Hadamard gate. And then we want to get x1 from this state, but first we need to remove x3 and x2. Again, if x2 and or x3 equals 0, then this is a moot point, but if they're both equal to 1, then the controlled rotations are going to remove these, and then at this state, what we have is 0 plus exponential 2i pi 0.x1, and this, after a call of the Hadamard transform, gives us x1, okay? So here we have the case of 3 qubits, and it's easily generalizable for the case of n qubits. Now, like I said at the very beginning of this lecture, one of the main appeals of studying the case of the algorithm for quantum phase estimation within a module dedicated to quantum factoring algorithms because it gives us an opportunity to introduce the quantum Fourier transform. The quantum Fourier transform is the inverse of the circuit that we just created. So the circuit that solves the quantum phase estimation problem is going to be the inverse, is by definition the inverse of the quantum Fourier transform. So this is what we have here for the circuit that we just created, and then the inverse of that is simply the quantum Fourier transform. Now, what does the quantum Fourier transform look? Well, then, what does it look like? Well, what we said, we know its inverse. So really, what we can do is just look at the circuit in reverse, okay? And you see here the only main difference is that it's no longer the inverse of rotations, but just the rotations themselves. But otherwise, this is just the same circuit as before, but seen in reverse, okay? And this is the circuit for the quantum Fourier transform. We're going to be reusing it when we study Shor's algorithm. Note that one very important case for us, though, is that our circuit, we know how to apply it from any given basis states. And that part is really important for the case of approximating a phase that is not a rational phase. Okay, so our quantum, the inverse, so the circuit that we just created, acts this way on the basis states. So why do we care about what happens on the basis states? Because in the case of an arbitrary phase estimation, what we need to do is we need to be able to distribute the action. So now we're calling our circuit inverse of quantum Fourier transform, okay? But this is just the quantum phase estimation circuit, okay? But we like to have it under the perspective of quantum Fourier transform. So it's just its inverse. And what we need to do then is we're gonna pretend that everything is the same, okay? So we have this circuit that gives us the phase exactly when the phase is a rational number. Now, when the phase is not a rational number, we just pretend everything is the same. And what we hope to measure in the end is something is close enough, okay? So when we apply the inverse of quantum Fourier transform psi, we need to know by linearity, we need to know the action on each of these y's, okay? And this is, of course, given here by the expression that we had in the previous slide. And if we reorder the sum, this is what we get here. And what's really, so we define here the x, so this is the x that we want to measure, okay? X is the rounding of 2 to the n times omega, because then x over 2 to the n is going to be close to omega, okay? So that is the x that we hope to measure, but we are not guaranteed to measure it. As you can see, some other k's have non-zero coefficients here, so you could end up measuring them as well. But so here, as I said, this is the x you want to measure, and this is the probability of measuring it. So 1 over 2 to the n times the modulo square of the sum. It turns out that you can show that the probability is superior to 4 over pi square. So what does this mean for us? What it means is that we will not succeed all the time, right? We have a constant probability of succeeding. Now, the growth, the size of our input is proportional to n. So this probability of success does not even depend on n, which means you can repeat the experiment if you fail. Okay, so if you fail, you repeat the experiment, and the chances of failing all the time become very low as you repeat many experiments. Okay, so this is the case with many quantum algorithms, that they do not necessarily give us the right answer, but we know a lower bound on the probability of success. This one here is a very good lower bound because it's constant. It does not depend on the size of the input. Now, a last point that we want to make in this lecture is that there is another source of error that is often sort of swept under the rug. It's the fact that we don't know our rotations gate. In general, we don't know our rotation gates exactly, but rather up to an approximation factor, because we've had to approximate them through the Solovay-Kitaev algorithm, for example. So what does this mean? This means that in theory, you have to also worry about the fact that so if this is your exact QFT, so exact Fourier transform, the one that we've used to analyze the algorithm, then it's at a certain distance. What we really have is this, an approximate QFT, which is at a certain distance from the ideal QFT, and every probability that we're gonna have at measuring the input is going to have is going to be deteriorated. It's going to be a little bit further away from the actual probability of measuring a certain outcome had we had used the exact QFT. But it turns out that if we have this approximation factor, so epsilon equals 1 over a polynomial in n, then the distance is going to be here n squared divided by that polynomial of n. So, for example, if you get a polynomial of degree 3, so if your approximation grows as 1 over a polynomial in n of degree 3, then this thing is going to be growing, it's going to go to 0 very rapidly, and you will effectively observe very little difference in the probability of success. So what it means is, with the right amount of approximation on the rotations, then the probability of success that we've seen before, the 4 over pi square. So this is going to be, what we're going to observe is going to be something that asymptotically will tend to this value, okay? So all we have to do is approximate our rotations with the right approximation factor. So this is all for quantum phase estimation. And remember, the important takeaway here is that it introduces the notion of quantum Fourier transform, which is going to be a key element in Scholl's algorithm. Thank you very much.